Okay. Prarambham kurmah. Vakratunda Mahakaya Suryakoti Samaprabha Nirvignam Kuru Me Deva Sarvakaryeshu Sarvada Gurur Brahma Gurur Vishnu Gurur Devu Maheshwaraha Gurur Sakshat Parabrahma Tasmai Shri Gurave Namaha Saraswati Namastubhyam Kam Varade Kamarupini Vidyarambam Karishyami Siddhir Bhavatu Me Sada. Okay. So now today I actually got a little bit, I found that do good tutorial, some visualizations. I thought I'll actually set up the stuff. I'm almost there. Not so there is some to look at. Some how do I put it? A little bit not so. It's a decent visualization, but I was trying to get something more interesting that you can actually set up and look at and be interactive. Couldn't get that to work yet. I'm probably this close. So next class, I'll probably just create that and give you guys access and see if you can start using that. Okay, so let's do this. Let me share the screen. Are you able to see my screen?
Yes.
Okay, cool. Yeah, okay, good.
4 blue dots at the top.
Top, right? Are you able to read it?
Yes.
Okay, so let me see if I can magnify it. I see it is just the. So actually, this is a little bit better than actually me writing it down. And so that way we can extend this and then kind of look into it a little bit more multiple dimensions. So basically, how do we visualize dimensionality? Okay. So all of us have read about matrices, right? So we have dealt with 1 cross n, where the first, any matrix is essentially depicted by m cross n, right? It has m rows and n columns, right? So think of it like this. If there are 100 words in a dictionary, you will have 100 rows, and based on how rich your embeddings are, let's say you are able, and you will have as many number of columns. Okay. So the number of words is going to be primarily dependent on how many words you have in the dictionary, right? And the number of columns, we will actually go one step at a time. We'll go with 2 columns, just very something simple. And from there, we can start extending it to extending the dimensionality of these embeddings to something really large. Okay, so that way it will help us build it one step at a time to be able to visualize it, which is what is more important. Okay, so you might have actually gotten a kind of a gist of the concept in there. Priyamadya, I have actually uploaded the video. I think I did it last night or this morning, something like that. I completely forgot about it. So hopefully it is a part of that playlist.
Okay, no worries, sir. I'll check it today. Yeah, I'll download it today. Thank
No
you, sir.
problem. No worries. Okay. So now if you look at it in this simple XY chart, right? The gender is on the x-axis and age is on the y-axis. So we have 2 dimensions. We are using 2 axes, right? So if you look at it, let's look at the y column, the y-axis. The y-axis depicts age, right? Lower the number, lower the age, higher the number, higher the age, right? So we have taken just 4 terms, which is a subset of what we kind of dealt with last week, right? So we have man, woman, boy, girl. So here, if you look at it, so we are going to use some lower number for the male gender, some higher number for the female gender. So obviously, if you look at it, so as the gender goes from left to right, so the more masculine words will be on the left, more feminine words will be on the right, more neutral words will be in the center. Okay, just think of it like that. And in the y-axis, younger terms that basically get referred to some younger generation will be more closer to the x-axis in this case, and as the age increases, it'll essentially diverge from the y-axis. So if you look at, let's take just the two dots on the left, right, boy and a man. So both are masculine. So there is a value 1, and the age is 2 and 7 in this case, where boy is not too small, right? So if you look at, if we actually have, let's say, much small, like if, let's say, if you had more, let's say, baby boy might actually be even lower than this. And let's say in this case, anything that we use so basically man is an adult, and let's say we pick the value 7 for that in this case, right? So if you look at it, so boy is on the lower left corner. Above that is man, because same gender, higher age. So between boy and girl, it is the same age but a different gender. So one correlates on the y-axis, one correlates on the x-axis. So if you compare boy and a woman, so it is both have a higher age and also a different gender. So it is diametrically opposite. Right? Are you guys able to understand this part? So these four dots, how we have represented in this diagram, right? Now, so now that is what we have represented in terms of some numbers. So actually last week I started with numbers and then tried to explain it. Now we'll actually start from the visualization and then assign some numbers based on that and try and take it one step at a time. So now if you look at it, so one word that I used last week was a person, right? A person is something that is not too old, but at the same time not too young either. And it is a neutral word that we use, right? We don't, when we say I saw a person, it doesn't depict either masculine or feminine in this case, right? So if you look at it, that will likely end up being somewhere in between, probably a value of 5. And based on, let's say, if it is a child versus a person, so child might be a lower age, person will be a higher age, but it will be in the right smack in the center of the gender. So maybe a value of 5, and each of these terms will actually start going up in the ladder, right? So, but let's take one simple example where we have the same gender but a higher age. Can you guys think of some word? So masculine gender but a higher age than a man.
Old person.
Yes, yeah, old person will be a neutral gender. So probably grandfather is essentially masculine and definitely more than a man, right? So that word will likely go over here somewhere at 9. And obviously grandmother will end up being slightly above woman, but at gender value being 9, right? So which is what we are going to see. So if you want to map grandfather, the grandfather will essentially be above man. And we said, okay, infant, child is a little bit higher, adult is essentially same as a man, right? So if you look at it, so those three words go right smack in the center. So we are able to represent how many words in this case? 4 plus 4, 8 words with just two axes. Because, and they are related words, but they have subtle, no two dots are in the same place. That is the important thing to notice here. But you are able to find a place, some place in this whole graph, and you are able to assign a coordinate for it, right? So whatever number that is there in the right ends up being xy coordinates, right? Gender being x-axis, age being y-axis. And you can fit even more, right? So if you look at it, so yeah, they've added a little bit more, right? A teenager, which is somewhere in between a grandmother, a grandparent, and an octogenarian. Octogenarian is somebody who is in their 80s, right? So we are able to fit so many words in this domain.
Octogenarian is what, sir?
Yeah, go ahead.
Octogenarian, the word you said, what is it?
Octogenarian is somebody in their 80s. Octal is 8, right? Octogenarian is generally, but
Okay.
it is also used in a slightly general sense where somebody who's really old,
Okay,
right, in
thanks,
the
sir.
80s. Right? So in Sanskritam, if you say, it is a Vriddha, right? Somebody who's really old, right? So that's kind of what is called octogen. Now, if you look at it, so just with 2 axes, we are able to start putting in more words in the same plane. Okay, good. So now let's add the other 4 words that we spoke about last week: king, queen, prince, and princess. So if you look at it, all of them have some sense of royalty to it. But none of the words that we just mapped does not have any royalty associated with it, right? They are normal, common people and they don't have any royalty associated with it, right? So now if you introduce the new set of words like king, queen, prince, princess, let's say a minister, maybe things like that, now you will get to a point where you actually need another axis. Let's say in this case we call it a z axis, right, to be able to represent these 4 words. So if you look at it, so we have mapped a 3-dimensional word, a 3-dimensional axis in a 2-dimensional space. Are you guys able to look at it and visualize in 3 dimension this axis? The diagram that I am showing, right? So we have introduced a 3rd axis, right? So there is a royalty over here. So now if you look at it, as the royalty increases from 0 to 10, you will see the royalty of the words that has higher royalty will essentially go more towards the deeper end, and whatever is not royal will actually stay closer and in the shallow side of it, very closer to the value 0. So if you look at it, so king, queen or higher age, different gender and a higher royalty. So if you look at it, prince, if you look at it from a 2 dimension, prince, princess will essentially align with boy and girl. King, queen will perfectly align with man and woman. So if you just go back and map those words to this, they will exactly sit on top of those 4 dots, right? Prince will sit on top of boy, girl will sit on top of, basically princess will sit on top of girl, and then king and queen will obviously sit on top of man and woman, right? So that is why we need a 3rd axis now, where you can separate them spatially in the 3rd axis. Boy and prince are separated on the 3rd axis. King and queen with my king and man along same gender but depth in royalty. Woman and queen same again, same gender, depth in royalty, right? So now we needed a 3rd axis to represent another attribute to represent these words, in this case being royalty. So far so good? All right.
Yes.
So, okay. So this is what is called a representation called embeddings. So what you do is, so for the models to understand the concept of a word, what you do is you basically represent the attributes of a word across multiple dimensions and represent them as these list of numbers. So in some sense, if you have, when ChatGPT, when you actually give these words to ChatGPT, they don't understand the word themselves. The words have a representation in this vector space. So we call them as vectors, right? We have seen anybody I think we read vectors in 12th grade, right? 11th or 12th grade. Vector, we talk about vector algebra, right? Or coordinate geometry in this case, right? So coordinates, vectors can be mapped to coordinates and we can understand them as coordinates, right? So all the 3 axes. So 3 axes, and you can use them and you can map it to this and we are able to understand that, right? So these embeddings are nothing but representation of these characters as numerals, and now the model can understand how they are related using these numbers. Okay. So this is what I was explaining last week, where initially what we did was, in this case, let's say there are 8 words. We were using 8 columns and we were using a 0 or a 1 to depict which word are we really referring to. So if we had, let's say, 32K words in a dictionary, we will have 32K dimensions in those cases. And for each of those words, one of those dimensions will be 1 and the other all dimensions else will all be 0, which was really too many waste of those dimensions in terms of representation. But if those dimensions are assigned to these attributes of these words, what is the first advantage? The first advantage is it reduces the dimension, definitely, right? But it also gives us an understanding of semantics. Semantics meaning of these words, and we can actually do some arithmetic like matrices to essentially do these mathematical calculations and understand. So let's say if you are able to ask a question to ChatGPT, if man is to woman, what is it for boy? Then it will be able to give an answer as girl. So what is essentially doing is, it's basically saying, oh, I have man and a woman and I'm trying to find out what it is for boy. So if I find the relationship between, so the only dimension where this varies is in the gender, right? 9 is to 9 and 1. So in this case, I have boy. So if I subtract it, there is 8. So if I add 8 to the boy, I get 9, and the rest of the 2 dimensions of the boy remains the same. So now let me go back into my vector space and find out what. So now it takes 9, 2 and 1. And it says, oh, okay, I take 9 for the gender, right? And 2 for the age and 1 for royalty, right? Now if I take that, what word comes closer? So it will essentially pick a vector number that where we have this girl sphere, right? There is a sphere for the girl over here. It will essentially bring us close to it. You see what I'm saying? So this is essentially the concept of embeddings. Okay. So now the question is, how do we come up with these numbers? Right now, let's say I take another 4 set of words: India, Delhi, right, and Pakistan and Islamabad, right? So the moment we say these 4 words, our minds can come up with what is the relationship between these words, right? So now, if you look at it, if I take 2 more dimensions to represent them, what would be those 2 dimensions? One dimension would be
Country and capital.
perfect. So country will be 1. So for different countries, maybe based on their geographical distances, we could actually assign some numbers. We can take one reference. Let's say we are Indians and we basically use India as a value 0. Then anything in terms of distance to these countries, we can either take positive and negative distances and figure out, oh, below the equator is some negative, above India in terms of the globe is positive, and we take some distances and we can actually map all the countries along that vector, right? And then what we'll do is, this is name of the countries, right? And then for the capitals, you will take a completely different dimension, and those dimension, the value for the country will all be zeros, right? For capital again, corresponding, so if let's say you had India as some value, you will have the same value for the, let's say in this case, place and capitals, right? So country and capital will be in the same dimension. So which, let's say 0 for the capital, 1 for the country, right? And that's it. So we could actually have other numbers assigned for other attributes. Let's say I talk about specific some cities, let's say other than Delhi, right? In this case, let's say we talk about Mumbai, Kolkata, or Chennai. These are other cities. That's about it, right? They are not capital. So I can actually use a different number. Let's say in this case, I take a number 5, right? Countries, or let's say if I'm trying to associate the spread of the geographical area that it covers. A country is usually bigger compared to its own capital, and I can use that as a representation in one axis and be able to visualize them, right? So now, but the thing is, the important takeaway here is these are two dimensions that we haven't even considered for these set of 8 words. But if we put all of these words into one dimension space, now we will have total of 5 dimensions where think of it like in the highest level, whatever we talked about initially, man, woman, boy, girl are all living things, and in terms of the country and capitals are non-living things. So what I would do, so for all the other two dimensions, the value for man, woman will all be zeros, right? Where and the values for gender, age, royalty will all be zeros for those countries and capitals, right? So now I've increased it to 5 dimensions. Now I can keep increasing these dimensions depending on how many words I'm bringing in and in what aspect these words differ against them, right? So far so good?
Yes.
Okay.
Yes.
So now, important question is, if this is what we are going to do, this is going to be an extremely laborious process because let's say one of the embedding representations that we have trained has close to 400,000 words just in English. And think of supporting all other languages across the world. So it is said to be that there is we had close to probably 12 to 15,000 languages. And in fact, as a matter of fact, we are losing 100 to 200 languages on a yearly basis. Some of them are aboriginal languages, and we are actually losing them. So there is actually a very interesting talk by a lady who works for this institution called Endangered Language Studies or something, and they are funded by this Endangered Language Fund, and it talks about different languages. I think I spoke about this in my very first class, right? So where there are languages where they don't have concept of um, relative directions, they don't have left, right, front, back, on, top, down. They all always refer to like northwest, east, south. That's about it. So they don't actually have the other concept at all. So they always use literal directions because they are aboriginals, they are going around all the place. So so now coming back to this, now if you take all languages and all words, now look at how many different words we are having. So if you put all of them into one, we already know there is one additional dimension I need to add, which is the language dimension, right? So, and then between that, I could actually have very many things associated with it. For now, the dimension of the languages, I have to assign values based on how related these languages are. For example, all the languages emanating out of Sanskritam will probably have closer values, right? And even there, you might probably have the South Indian languages which have a lot more similarity tied closer compared to let's say maybe Marathi and let's say so Gujarati. Do we have common words between Marathi and Gujarati?
Yes.
Yeah. Yes.
So I'm assuming they are more related compared to comparing them with either Tamil or Telugu, right? Right? It
Yeah.
is it
Yes,
safe to
yes.
say? Yeah.
Yeah.
Okay. So now if you look at it, right, so then you can assign numbers for these letters in there. And English can be completely different, and Chinese can be completely in a completely different realm, right? So now this is way we can actually keep expanding the dimensions. And today, some of the complex models take a guess on how many how many dimensions that we use. And remember that these dimensions that we are talking about these are actually decimal values. They are not absolute integers either. So now a scale that can take decimal places and the total number of dimensions. If you can kind of take all this into account, can you just come up with an educated guess on how many dimensions that we might be dealing with these days?
So each dimension is a decimal. That's what you're telling.
So each values within the dimension is a decimal. So here we used integers, right, from a value of 0 to 9.
Okay.
So
And
those
your question is
values
how many such dimensions?
yes. You might think,
Multi-dimension?
come again?
Multi-dimensions?
Yeah, how many dimensions do you think we may have for, let's say, ChatGPT, right? How many
Maybe
dimensions might be using?
maybe 10,000 or something.
I
So
think more.
actually, it's not that bad if you look at it. So there, it uses close to three. So one of the large models uses 3072 dimensions, and if you look at it, even with simple 300 dimensions, so you look at it, right? The amount of space you got with going from 2 to 3 dimensions is plenty, right? So, and another thing you have to remember is you don't have to completely assign that whole dimension to royalty. So royalty could be assigned. So let's say if you think of it as a box, right? I can say royalty can be a corner in the box, right? And then let's say if I'm going to take another concept, maybe poverty can be the other end of the box, right? So anything that has a little bit of poverty associated with it can go to the other end of the corner, and anything with royalty can go to the other one of the other corners of the box, in some sense, right? So now I don't need to create another new dimension for poverty. Given more flexibility in assigning values for the dimensions, I can actually push them to 2 different corners and actually reduce the number of dimensions I need to deal with, right? So now if I add a fourth dimension and fifth and sixth, the amount of usable space, so to say, I can get can be, it can be humongous, right? And then what we can do is we can further, so that way we don't have to keep expanding them. So there are, for example, um, to get reasonable results in terms of this translation quality and stuff like that, somewhere around some of the models uses somewhere around 768, or think of it like 750 dimensions. 750 dimensions gives you pretty good results, right? Now, how do we actually come up with these dimensions and we assign them, right? So far so good. We talked about how we can increase the dimensions and how we can increase the granularity in the dimensions and how can we spread and increase the number of dimensions as well. Now the question is, how do we actually build these dimensions? How get these values for these words? So there is actually a guy called who was a linguistic, I think. I don't know whether they refer that guy. There's a guy by name JL Perth. Actually, you know what? The other blog. So I have another blog. I actually have these lists in the document that I sent in the very first class. You remember? Let me see if I can find that actually, because this particular quote is yeah. Do you hear this? The highlighted. So this guy actually said in a very simple way, you shall know a word by the company it keeps. So basically, you don't, when you actually frame a sentence, you relate these words in a slightly different way. How do we actually do Anvayakrama, right? So we first take a Kriya Padam, so which is essentially the verb, and try and associate subject, object, and all the other words that glue these three things together, right? So with Kriyapadam, we actually have the tense. With the words, we get genders. So basically, all the variations that a vibhakti gives, right? So it gives you singular, plural. It gives you different basically vibhakti rupams, which basically tells how are these words associated, and on top of it, it also gives you what gender they are, right? They are whether neuter, masculine, or feminine, right? So with these things, you can actually kind of get a lot of this information when you put them as sentences, right? So now if you start taking it from there, then what ends up happening here is you can just use on the probabilities of how probable are you to see these two words in the same sentence. You can use that as a definition of probability and start coming up with these numbers. That was the original method. So what we started doing initially was, so use this as a measure of probability, and use this so what we would do is how probable, let's say you take let's say you say, okay, within these 10 words, if I take 10 words at a time, and if I take 10 words at a time, and and I start taking all the words that I see in that window and assigning them relative probabilities in the positive, and things that I don't see them, if I start assigning probabilities in the negative, then I can start assigning relative probability, right? Once I start assigning relative probabilities, then what ends up happening is then I can actually use these probabilities to calculate these different dimensional values. So based on this, there are certain methods. We may not have enough time. I mean, it gets a little bit deeper to go into. So I can actually send you the paper. I have the paper. I'll have the paper listed in that document. So if you have interest, you can just go take a look at it and see deeper to figure out what they are and all that stuff. How they are, how you actually come up with these dimensions, and how we can come up with these numbers. Right. So now let me do this. Let me show you one of these things that you can actually look and see. So what actually Google did was, so let me stop this. So this is the website. You can even go to this website, projector.tensorflow.org. I think I have that in the document as well. So I can actually cut and paste this in the chat if you guys want to take a look at. And if you look at it, so it has 10K. So you can even load the total. In this case, this vector is, so if you look at it, this is 71,000 words, and each word has 200 dimensions. So what we just loaded is around word to like 10,000, which is 10,000 words and 200 dimensions each. So you can actually, oh, not this. You can do the same thing for images too. We will come to this part. I will actually talk about that as well.
I have a question here. So, like, how are they able to show 200 dimensions in just 3D?
So, good point. I'll come to that. It's actually a very important question. I will talk about it, and so I'll actually initially talk about it. So, have you heard of something called principal component analysis? You were in mute, Madhya.
Yeah, I think I have heard, not
Oh.
really sure, but
I'll cover this. I'll cover this in a slightly different way. There are certain things. There are something called transformations, a concept of transformations. We can do those transformations to actually start reducing the dimensionality and find what is the minimum number of dimensions that you need. So what you can do is, so let me start with this, right? So you can say, okay, I know my word set, my dictionary has a very rich set of words. So I'm going to use the probabilities to calculate it, but I'll initially come up with some numbers. Let's say I will start with 3000 dimensions. I know my language is so rich that it needs 3000 dimensions to capture all the variations. What I can do is I can actually come up with with 3000 dimensions, and then do this calculation called principal component analysis, and then find out what is the minimum number of dimensions that I need to capture, let's say, 95% of the variations in these words, right? So then I can actually find out. So if you look at it here, let me show you on the left hand side. It doesn't show that anymore. Why? Here, if you look at it, right? So this, we just saw it was 200 dimensions, right? If you look at the number 1, 2, 3, 4 and all these numbers, so what it says is how much of variations or the distance variations it is captured by dimension 1, whichever number it picked. So it essentially, the dimension that captures the highest variations is essentially, it is sorted in that order. So it calculates the PCA, what is called the principal component analysis, and then finds out so basically it sorts them based on those dimensions that captures the maximum variation. So if you look at it with going back to the old example, right? Royalty is a very weak dimension, right? But whereas if you look at it, age and gender are very rich dimensions. You can capture a lot. So in fact, it turns down, right? The very first, when we started, we were able to fit in like 10 words in that just two dimensions. But whereas if we had started with age and royalty, we may not have been able to capture as many words that we originally were able to with those two dimensions, right? So now if you look at it, age is a very rich dimension, gender is a very rich dimension, right? uh, and but whereas royalty is not as much, right? So let's say when it comes to verb, level of motion, right, can be a dimension that captures a lot of information, right? So emotions and the locomotion kind of, or the movement, these two can be two dimensions for the verbs that can carry a lot of variations, right? So let's say whether this emotion captures positivity or negativity, right? And whether this movement captures staticness or movement. If I take just these two as attributes and start mapping all the verbs in there, I might be able to fit all the verbs in those two dimensions in a pretty good way. It may not capture all the variations, but I may be able to capture a lot more, right? With these two in terms of verbs, right? So verbs can, so that way coming up with these actually makes a huge difference. So now just hold on to that thought. I will come back and briefly touch upon it, and we can actually cover it in great details in the next class if you are interested. Okay. Because there is something called non-linear transformations, can be linear or non-linear. Okay, linear transformations cannot bring it down, because linear is basically, what I'm saying is, I can rotate, I can shrink, and these are the two things that I can do. I can stretch, let's say, I can stretch and compress, I can rotate. Okay, and if these are the only two things that I can capture, that is kind of, think of it like linear transformations. But let's say if I can find out, let's say there is a small cluster of words and I want to squeeze them into one, and I squeeze the other one towards the other direction, then I'm actually doing two different operations on two different clusters of words, right? And this can only be possible with non-linear transformations. What I'm doing is, I'm not doing the exact same operation on all words. I'm doing a slightly different operation on different directions on these two different words. So if you look at it, there is, you see a column heading called UMAP and TSNE. These are two other different ways of reducing these dimensions. So now let's go and look at it, right? So you can go to the search, and if I can type king, right? So this is basically word matches in terms of substring matches. I have to select. If I select king, so now it says, so that basically gives you what it is. And if you start looking at the nearest points, I'll come to how you are calculating the nearest points in a moment. Next. So if you look at it, kings is actually the most related word, with 0.338 being the distance from it. So I think this is essentially a normalized scale from 0 to 1. So no word is more than 1. So let's say if you compressed all of it, let's say if you go to the 3-dimension thing, if you divide all the columns by 10, you will get a number from 0 to 1, right? It's actually called normalization. And if you are interested, we'll take one class just walking through all these statistical concepts separately. We'll start from something simple and we can go all the way up to it. So now if you look at it, kings is the closest word. Then you see queen, you see son, Henry, throne, emperor, prince, England. Obviously, England is associated more with this monarchy right now, right? So then kingdom, reign. So this Roman numerals are associated because we have heard of these names of kings like King Louis the Fourth, King Louis the Seventh, Eighth, and what all numbers. So all these Roman numerals are associated with these king names. That's why you see all these Roman numerals. Then you say ruler, Scotland, and all that stuff. If you take, let's say, we'll call it India, right? So if you take India as a word, you will start seeing all the names of these places starting to show up. China is something because probably there is today in today's news, you may actually be seeing India and China compared against each other in a big way. So you have a higher probability of seeing China in the same statement when we talk about India, right? So that's why that shows. Then you have Pakistan, Indian, obviously, right? So so India, more related word is Indian in that sense. And then Africa, Australia, all these country names, Asia as a continent that encompasses India. Then you see Bangladesh, Malaysia. You see most of these countries are they are more closer in terms of geographical proximity as well. If I take USA, you will see the words of, so now look at those words, right? Canada, Australia, America. Probably I should see Mexico somewhere. And then if you start looking at it, you are seeing Germany, because some of the European countries start coming into play here. United States, you can see commercial and things like that. Let's say, let's take, um, give me an example of a word that has a completely different kind of connotation to it. Let's say we take color, right? In this case. So you take red. You're able to see my screen, right? So if you take red, if I you see all the colors, related colors starting to show. Blue, white, green, yellow, black, dark, purple. See, oh, this is interesting, right? It says dark is associated with red. So dark and light are essentially words that don't in itself represent any color. It basically gives you the shade of the color, right? But still, those related words are starting to show up. Purple, brown, so color in itself as a word associated with it. Pink, gray, dead.
How come and cross are there?
There will be some false positives. There is actually another concept called TF-IDF. I will talk about that. So if you want to talk about NLP concepts, right, I will talk about it in one class. How, so this particular dictionary is not TF-IDF normalized, is what I would think. So TF-IDF, what it will do is it will also take into account the frequency at which these words occur. So we can talk most of these concepts, right? You can actually come up with some general commonsensical way of intuitively understanding it. So I can actually come up with some of these terms. And so if you're more interested in the NLP side of things, I can kind of walk through that and have you more be familiarized with those terms so that you can start reading about it and stuff like that. So if you look at this, these are essentially words that you can start associating them. So let's say take fruits, right? Let's say we have mango. Wow, interesting. Actually, we should also talk about some of these things. If you look at it, the name of all those fruits that we know that it actually shows up in here are all more Western words, even though I used mango, which is one of kind of more consumed fruit in India compared to here. Wanton quince is a fruit here. Koa, Afonso.
Most of that name I'm not even aware.
Yeah. See, I think some of them, you will also have false positives. Assume one of the important things is, right, you will have some level of positive, because this is not, we didn't, see, if we took the manual approach, you will very carefully put them together, but that is not practically possible, right? So we come up with this, and this is also, I think this is word to vec. There is another model called glove, which is just pure probability based on how often you see these words. Word to vec is a little bit more informed model. Let's see whether the glove is here. Oh, they haven't have the glove yet. I can actually download it and upload them. That's actually, so you can also upload them, which is what I did. And just as a teaser, I can show you something. What is the time? 6:60. So I did it for, oh, where did I go? Oh, I have it on a different window. I'll show it to you. So because that is actually running on my local machine. So I don't have it in here, but that's okay. I can actually bring it down and show it to you later. So if you look at it, So you can see all this. Let's see whether they have fruits. See, they don't have Indian fruits in there. And remember, this is not all the possible words. This is 70K words that they came up with, right? So whatever is the abridged versions of that. And I'm sure the dictionary of some of the recent dictionaries, the way we actually look at words have also changed over a period of time. So what I will do is I'll actually go through with this set of, so we will talk about this going back to what is this relevance of this with the words and the pratyahara and all the stuff that we did and how we can model them, and then come back to actually probably talking about what is the relevance of embeddings with reference to Sanskrit today and why should we be aware of it. Okay, I'll probably have more of a kind of an awareness kind of a talk. So I think from what, let me take a note. So you wanted one where it's more of a statistical terms and other stuff, huh? Is that what you wanted?
No, not really. Statistical and other things I'm aware more or less.
No, what I'm saying is about so you said how do you reduce dimensions and things like that, right? Have you heard of these terms like TF-IDF?
Again,
Term frequency, inverse document frequency.
come again, what was that?
Term frequency, inverse document frequency, TF-IDF, then concept of what you call as um, uh, how do we normalization, standardization. These probably you might
Yeah,
have heard.
normalization and other things I've heard, and reduction of dimensions also I've heard.
So yeah, have I heard of linear and nonlinear transformations?
Yeah, that I've heard.
So do you understand them?
Yeah,
I
in
can
fact,
briefly talk about it. It's not going to be too deep. So one of the important things, if you really start wanting to get into the world of like of AI and machine learning, right? Most of the models today, you can it is good important to understand the intuition behind it rather than the actual mathematics. So even when I present in other concepts, whenever, okay, let's say we have some ideas on the cybersecurity that I present, or in terms of this, even in this cross-lingual methodology as well, when I present, I always use those analogies to compare against them.
mm.
So, and
So,
we can just quickly cover this, maybe take 10-15 minutes on one of these presentations and walk over them and talk
correct.
about it.
You may do that. The reason why I was telling, because in fact, in my master's, I have done various courses on natural
Good.
language, neural networks, and various other things.
Oh, good. So
So,
then you will get most of that then.
so that's why. So it's just that it is more than 25 years. So I don't
Yeah.
remember much because I have not been using them. So, but
Yes.
I'm like, that's why it makes sense. Like, I know something like that. Yeah.
Right. Oh, okay. That's good. So see, there are some. See, the thing is, if you have those intuitions, it's actually easy to get on board and start doing them and understanding them pretty well. So things like what is called this topic modeling. These are some of the very rudimentary concepts that you start use on NLP. And
Mhm.
embedding is actually kind of comes way later in the game, but it is more intuitive to understand rather than the other concepts.
Correct. In fact, when you talked about all this parameterization and other things, right?
Right?
So I remember I was I keep on doing a lot of experiments myself. So I was trying something. And I actually was categorizing it based on some properties and things like that. It's just
Mm.
that I came to know, okay, we call them embeddings. Okay, just now with your thing.
Ah, okay. So
Okay.
embedding, see, currently these days, what we originally called as embeddings in let's say in the early days, meaning 2015, 2016, and then what we actually call embeddings now embeddings is actually a loose term. So
Mhm.
embeddings can be any bunch of numbers that captures some attributes of these input or output or any of these words like this. So for
Correct.
the prompts or anything of that sort. In some cases where you actually pick up these vectors, can be anywhere in this model architecture. It could be in the input. Initially, it used to be an input mapping explicitly in NLP, in NLP lingo. And the way you used to train them was quite explicit and all that stuff. Now, to some extent, what we do is embeddings are also, for example, for the images and stuff. So if you look at, you reduce them and you basically finally come up with, let's say, an array of 1,000 numbers, which you use that using something called a softmax function to find out maximize among this what is the which has the highest what is the, on which one of them will you actually assign the maximum probability. So there is something called a softmax function. So
Right.
so now they have started using embeddings as a term to capture whatever is the last but one layer in certain scenarios. So now these days embeddings is used as a very loose term, but conceptually you can still attach it to the same thing.
Okay.
So
And
now,
the reason I was telling that I'm familiar and things like that, these concepts, right? Now I remember there was one project which I did those days where basically given an active voice sentence, we need to convert into a passive voice and or the other way around kind of thing. So even to do that, obviously you need to capture a lot of properties of the words.
yeah.
So
So initially, then there used to be another term called natural language understanding, right? Where you would actually capture parts of speech, right? And other things as attributes, and then you use them to essentially do that. Where we would kind of do a little bit of manual infusion of these properties for the model to perform better, right? So the only difference between then and now, as what has happened is the models have become a lot better, and some of the ways on how we calculate error has become richer because our computational complexity can actually be made much higher because of the computational resources that we have today. So you
that is
can
all
actually define
correct.
a
That is
lot
also
more
there, and
complex.
also more data is available nowadays also,
Yes.
right?
So because of it actually goes back to how much compute, right? More data is more compute, right? So in fact, there is like in fact, the differentiation between ML and AI also came about how much data you use. So the more the data, the accuracy actually improves compared to the old ML models, which actually at some point it starts saturating. Any additional data would not give you because of those model architectures, because most of them, they were not highly nonlinear. They were nonlinear to a very small extent, but now these days the models are so huge and the amount of nonlinearity is like beyond proportions. Because of that, it can pack a lot of data in them. So in fact, there were some adversarial attacks on these models where you can actually have these models spit out some parts of your training data which can have some personal information in them. So this is another dimensions to this whole the whole AI side of things, where you can attack them, and also sometimes you can actually like for example, specifically in the areas of for driving autonomous driving and stuff like that, where you can, for the human eye, you will still perceive it as the same sign, but with very little noise in right places, you can make, I mean, there was attacks where you can actually make the stop sign to be read as a 45 miles per hour speed limit sign, which can be really detrimental, right? So where you are supposed to stop and somebody is crossing the road, and if you are making the car with that, you are essentially poisoning the data a little bit, where visually it doesn't make a difference to a human eye, but if it is interpreted as a 45 miles per hour name board, the car is going to essentially start picking up speed and probably is going to run over somebody, right? So there were a lot of research that happened in that area. So like going back to
But
that doctor nurse example, right? So there it was implicit bias. In this case, it is explicitly, if you know how the models are essentially using those minimas to understand, you can essentially force it to go through a different minima compared to the minima that you are supposed uh, to drive it towards, and make it infer completely something else. You'll see that the probability is a little over half, but the rest of the probabilities are so low that the softmax will actually project the 45 miles per hour sign as the most probable one compared to the rest. Probably what would have happened is the stop sign would have been probably a close second, but given that this is more probable, the model will predict this to be a 45 miles per hour sign compared to a stop sign. So things like that. So I mean, we are digressing now, but still now if you look at it, there can be things like that, right? So now before we are done today, there's two additional dimensions that I actually wanted to slightly touch base on. So I took this word plane, right? It's not, so if you look at it, there are multiple meanings you can give to it. One is an aeroplane, right? So where, which is related to flight and other things. The other thing is plane can be a Cartesian plane, like in mathematics where it is a 2D representation, right? If you look at it, then the words that are related to that would be the circles, rotation, surfaces, orbit, right? And you will see those. See, short is essentially more of a flight related. It's a word related to flights, right?
Correct.
Jet
Landing, carrying,
is landing,
are
all that.
also.
Angle is the angle of projection and things like that, carrying and all that. Whereas some of the other words can actually be, so once you start going down the list, it might be random words. So
Hmm.
first 10 for 10, 12 words are probably the most related ones and probably more closer to it as well. And then we are also using cosine distance. If we use Euclidean distance, you will see the distance separated a little bit higher. So that way you will be able to pick places on.
What did you? Oh, okay, okay.
I change the distance. So the way to look at Euclidean and cosine distances, right? So let's say you have it in 3 dimensions.
Hmm.
Cosine similarity is more about words that are on that same sphere. Let's say you have two words here and here. If you basically draw a circle, draw a sphere that brings both of them closer, what you are looking for is words on those sphere in some sense. Okay. Euclidean distance is basically you are taking a sphere and you are essentially putting those two words together in that sphere. And whichever words are within that sphere, which is probably in the surroundings, what are all the words that are nearest is what is being captured by the Euclidean distance.
Euclidean, I understand. What is cosine? I didn't get it.
Cosine is AB cos theta, right? So you basically your dot product, where what you are trying to do is what is the angle between these two words. So let's say if
Okay.
you take two vectors and lesser the angle, but it may be a little bit further separated away, but
Ah,
it's
okay, okay.
but it might be, so Euclidean distance may be higher, but the cosine distance may be zero because they are in the same axis.
Hmm.
On other axis, there is a huge distance. So if you look at it in terms of distribution, there are other things like Mahalanobis distance, and there are quite a few other distance measures that you could use to identify these similarities and things like that. So, and so this is getting into little bit of this embedding space where the
Hmm.
words are related, but they are related in two different contexts, right?
Okay.
So
So,
there are words like, let's say, sit. So one of the words in any dictionary that has most meaning is in English dictionary is the word set. If you look at set, you will see a lot of different. So you will see it starts becoming pretty incoherent because set has so many different meanings and it is used in, so it can be a sunset, right? And it could be words like set of all things, it could be a mathematical set, it could be yeah, kind of I'm set on doing
verb.
something, right?
It
It
could
could
be a
be
verb set.
verb set, right? Yeah, it could be a verb set. So now the set has so much dimensions, the if you look at it, the word starts to getting a little bit incoherent compared to the other words that we looked at,
Correct.
right? And now if you go, then, so for example, let's say you take the word he. Now, this word he becomes extremely contextual in terms of the content that you are reading. So that he, so let's say if you say, so you can say something like this. Krishna killed Jarashchandra and he did it to establish Dharma. Now the second sentence, he, if you don't have the understanding of the knowledge, you will be puzzled about whether to associate it with Jarachandra or Krishna. Right? So now we are getting into the world of what we call it as contextualized embeddings. And this, I will actually talk about it in terms of it has a lot of implications for us in Samskrita, in applying NLP for Samskrita. And we will talk about that. So we will have probably one lecture, just talk about different of these interesting topics, but it's something that people, I mean, the whole purpose of this class is to actually have people aware of it and start contributing towards some of the crowdsourced data sets that can help in cornering down this problem, that are very specific to Indian languages, more compared to the other languages that the NLP models support today. Okay, so this is one visualization that I actually wanted to show. So actually you can just play around with this. Projector-TensorFlow.org this is open source, and you can actually look around. There is actually, I also wanted to show something called what is called a vector database, and you can actually query them. So this whole arithmetics that I showed you, king minus man plus woman should give you queen, kind of that stuff. You can actually do some of those arithmetics, play around with it to see, get a little bit understanding of what these vectors mean and how they are related and stuff. And in fact, that is what one of these articles talk about in the big sense. So let's say if I have, yeah. So it starts with king, man, woman, right? If you look at the vector between king and man, you can make out the last two columns are the same. The first two columns are subtly different. Between man and woman, you see only one change. It's a pure gender difference, right? But between king and man, there are two dimensionality changes, like subtle changes in those, right? And there are many reasons for that, because you just cannot say, oh, man and king has to have the same value in terms of age, right? Man is, sometimes it's used in a very generalized sense, where it is could be an old man as well, right? So even though it is in the adult range, there is a little bit of variation in how the man is used compared to king. So if you get into the exact representations in terms of floating points, like decimal values, then these two words need not have the same value in the realm of age, right? It can be highly contextual again. That's where the subtle differences start showing up. And this is a good article to read. This is there in the link in the document that I shared initially. So these two articles, take a look at them. It's pretty interesting. And then we can come back. Probably, I'm not sure. Let me actually not. Let me stop the recording quickly, and then I just talk about the subsequent classes. Om Purnamada Purnamidam Purnat Purnamudachyate Purnasya Purnamadhaya Purnameva Vashishyate. Om Shanti Shanti Shanti. Stop.